Today we want to look at line integrals. Once again, we're combining the things that we looked at this week, the vector field and the parameterized curve, and we're integrating a vector field over a curve. So we want to make sure that the thing that's getting integrated is the vector field, and the curve is the set of values that we're plugging into the vector field when we think of integration that way. So just like in a single variable calculus integral, where we're integrating a function from a to b dx, where dx is a small bit of the interval from a to b, over which we assume the function is constant so that we can calculate area with multiplication. Similarly, we're integrating a vector field over a curve. We're going to break the curve into a bunch of directions, little signposts, dr, telling us which direction the curve is going. So the dr is a vector tangent to the curve c, and it's saying where the c is going. So we have all these different drs. So at this point, dr is pointing, let's say, that way. So at that point on the curve, dr is pointing this way. At this point on the curve, dr is pointing straight down. So we're describing the curve by saying what direction we're headed at any given point. Then we follow that direction, and then there's a new direction telling us which way we're going. We need vectors here for the dr because we're not just multiplying like in single variable calculus or with our double integrals or triple integrals. We need a dot product, and the dot product requires a pair of vectors, a vector from the vector field and a vector from the curve telling us which way we're going. So we're still just breaking up the curve into a bunch of different little directions, finding the dot product of the vector field at that point and the direction the curve is headed at that point, and then adding up all those values. Same thing that we did way back in single variable calculus when we first started integrating things. Any questions? So let's take a look at an example that's a little more complicated than yesterday. Yesterday we had a vector field that was constant, and we didn't really have to go very far in parameterizing the curve. I just needed some path to follow and do a bunch of dot products on. So let's increase the degree of difficulty. So let's suppose that our vector field f at x, y is, let's see, x plus y in the I direction plus y in the j direction. And let's suppose, so here's the vector field that we're going to be integrating. And let's suppose that c is going to be the quarter circle counterclockwise from the x-axis to the y-axis. So now our c is not just broken into two parts where it's just a couple of directions, all x direction, all y direction like we had yesterday. So pick quarter circle because that's the thing that we first start parameterizing. So our c, the function over which we are going to integrate, I've already messed up because you're supposed to draw the circle first. So we're going to go from the point 1, 0 to the point 0, 1. So we're going in this direction. And at each point along this curve, we're going to have to figure out what direction it's going with the dr. And we're going to find the dot product of the dr with our vector field. In this case, yesterday we had c going from just 1, 1 to 10, 1. So it's just moving along a line. Now, so it was all x direction, and then we turned and it was all y direction. Now we have a combination of those things. So what we need to do is parameterize the curve C. So we need to parameterize C. So we need to come up with a vector describing the position at a time t. And here's the reason that we picked a quarter circle. So to get from what we're doing is I just took a portion of the unit circle. So the x is cosine of t and y is sine of t. So that's just going to be cosine of t I plus sine of t j. And then t is going to go from 0 to pi over 2. That's going to give us that first quarter circle. So this is going to be, we're going to need this to tell us what those little pieces dr are. So here at 1, 0, our dr is going to be this little vertical one. There's dr at that point. And then at this point, dr is going to be going in that direction, dr. And we're going to find the dot product of these little drs and the vector field for all the points along this curve. Any questions? How's everybody okay? Everybody looks stunned because you just listed names, and the names are in a font that looks kind of stunned. There should be different fonts that mean different things. So like if you press the confused button, then the font looks all confused. And then if you have like a sleepy font, then your name just turns into a bunch of Z's. I know that there's got to be one out there because in very short time, it used to be that people had to would say things like, sarcasm doesn't translate over text, but now it does. We have a way to type it. The alternating capitals is just read as sarcasm now, just like all caps is now read as shouting. So we adapt very quickly to include tone in our text messages. Anyway, so I need these little drs, and so those are just going to be, we're going to get those by taking derivatives. So I just need r prime. So the derivative of cosine of t is minus sine of t. Plus derivative of sine is cosine. And this is all dt. So what we're doing is we're taking the derivative with respect to the components. So this is really the derivative with respect to r, and then we multiply by the derivative with respect to t. We can think of it that way if you're wondering where the dt come from. So the next thing we need to do is we need to make sure that the vector field, which is all these x's and y's, can communicate with the curve, which is parameterized with the parameter t. So now I need the vector field to be written in terms of t. So what we need to do is get the vector field to use the same parameter as the curve. Now we need to get the vector field to use the same parameter as the curve. It's not going to help if I have the vector field in terms of x and y, and the parameter, or actually these little directions, the dr, in terms of the parameter. Because now I've got, what am I integrating? The t, or how do I integrate these with respect to t? So, fortunately for our heroes, we've already done that in parameterizing this circle. So the way we parameterize this circle, x is the cosine of t, and y is the sine of t. So that is how we parameterize the curve. So if I want the vector field to communicate with our curve, I can use x is cosine of t and y is sine of t in the vector field. So I'll just rewrite the vector field as cosine of t plus sine of t times I plus y is sine of t. So sine of t times j. Now I have the vector field written in terms of the parameter. I've got the curve parameterized, and I've got the derivative. So I know my r prime of t, this is going to be my dr. Any questions? Let's actually perform this calculation because it's just going to be a dot product. So we're going to be integrating over the curve. Integrating the vector field, which is cosine of t plus sine of ti plus sine of t times j and the dot product of that and the r prime minus sine of t I plus cosine of t j dt. Now notice that this is an integral dt, so I need t values, but that was part of the parameterization. T goes from 0 to pi over 2. So this is a dot product. Before we integrate, we should figure out what this dot product is because that will give us a scalar. So let's calculate that. So we get, multiply the i's. So I have minus cosine t sine t plus sine squared t. So minus cosine t sine t plus sine, minus, yikes, minus sine squared t plus sine t cosine t. That's fine. So that's the dot product. The dot product is just a scalar. So we don't have any i's and j's anymore. The minus cosine t and the minus and the plus minus cosine t sine t and the plus cosine t sine t will cancel out. I can get rid of those. And we're just integrating a minus sine squared t. So this is all equal to the integral from 0 to pi over 2 of minus sine squared t dt. So you probably heard the sound of my calculator because we could integrate sine squared. We convert sine squared into cosine squared, convert the cosine squared into a cosine of 2t, and then integrate. Or we're more concerned with just coming up with values. We're more concerned with setting up the integral. Calc 2 is about evaluating this integral. Everything after Calc 2 is about finding out, using that integral. So I'm going to math 9 this, and I'm going to integrate the function. Oh, hang on. I'm in degrees. There we go. Integrate the function minus sine squared t, so sine of x squared with respect to x from 0 to pi over 2. So negative 0.785, which is looks like pi over 4. Yeah. I would probably, if this was like a test or something like that, that I actually asked you to do this, I would probably say round to the near to 5 significant figures because I like excessive amounts of significant figures. So it'd be like 78540. But let's just go with 3 for now. I only made the box big enough for 3. All right. Any questions on that calculation? So there's just a lot of setup in these line integrals. We have to be able to parameterize the curve. That's one thing. Then we have to write the function in terms of that parameterization. We got to get the function, the vector field has to be written in terms of the parameterization as well, so that the vector field and the curve can communicate in the integral. Then we're just calculating a dot product and evaluating an integral with only one variable. That shouldn't be surprising that we end up with an integral with only one variable, a single variable integral, because we're integrating along a one-dimensional thing. So we should expect only one dimension to show up in the integration. So we're not surprised by that. If you were surprised, you need to stop. It's expected. I'm just kidding. If you were surprised, like, oh, hey, this just works out to an integral of one variable. Well, yeah, you can be surprised by that. It's brand new. Here's the real reason that I did this example. Actually, this is not going to show up. Well, the real reason I did this example is that I have a picture of this example. So let me grab a picture. And share it. So here is a picture. We want to tie this to things that we were looking at before. And what we notice in the picture is that we see the curve going from 1, 0 along this quarter circle up to 0, 1. And we have a picture of this vector field, and we can see that the vector field is we can see that the curve is pushing against the vector field. It starts off kind of running perpendicular to the vector field, but then it kind of turns in, and the vector field is now pushing away against the curve. So based on this picture, with the curve pushing into the vector field, or the vector field going against the curve, thinking of it that way, think of this bird trying to make this turn in this wind. We should expect the line integral to be negative. And that's what we got. We got a negative pi over 4. Any questions? I knew the bird in the wind would show up today, so I'll probably be back on Tuesday as well. Any questions? Don't worry about the birds. I have a bunch of different birds that look very similar. So it's not like I just have one bird flying through the wind all the time. I have a whole bunch of different birds. They all look the same because I use corvids because they're smart enough to follow the instructions. And corvids are great because they're smarter than humans, so they can help me out with the math when I get stuck. Let's pause the video here. Yes. So the r prime, the dr that we need is just going to be r prime and then dt. So our integral dr gets rewritten when it's parameterized as a dt integral. R prime isn't r prime is the dr. All right, let's pause the video here. Talk about next steps.